Okay, let's look at friction when you're on a ramp. So recall we've looked at this situation before, where we have a block on a ramp and we want to analyze its acceleration. So find the acceleration of the block along the ramp with and without friction. So we're going to incorporate friction into this picture and see what happens. And we're also going to look at an example. So for a wooden block on a wooden ramp, with these respective coefficients of friction, would the block move if the angle were 15 degrees? Okay, so first, let's give ourselves a free body diagram. So we have the force of gravity pointing down. We're going to have the normal force perpendicular to the ramp. Now, since we're using this trick of tilting our coordinate system to make this a problem just in the x direction, let's draw in our components. Recognize this will be theta as well. If you imagine making theta smaller and smaller, you can see how both of those angles would close up. And this allows us to identify this component as mg sine theta, and this one as mg cosine theta. And first, let's look at the case without friction. So this should be review. And then we'll add friction in. So without friction, if we sum the forces, let's be meticulous and look at the forces in both x and y. If we sum the forces in x, what do we find? We have mg sine theta. The only component that's pointing along x, that'll equal the mass times the acceleration. And this is our familiar expression that the acceleration will go like g sine theta. And notice it doesn't depend on the mass. Now let's look in the y direction. This will be, we have the normal force pointing up. We have mg cosine theta pointing down. And this will sum to, so if this was in the x direction, this would sum to the acceleration in the y direction. But if it's resting on the surface, this will be 0. And this allows us to state what the normal force is, mg cosine theta. Okay, so this is the acceleration without friction. Now let's amend this picture and add in friction. So I'll draw it in another color to kind of hopefully make it stand out. So the force of friction is going to oppose the motion. So it would be a force, let me try and draw it nice. Here. Okay. So let's analyze the situation with friction. Now notice this is in the x direction, so it has no impact on the what's happening in y, so the normal force is the same. But in x, what will we have? We'll have the same mg sine theta, but now we have an additional component minus the force of friction, going to equal the mass times acceleration. And then we have to make use of our relationship that the force of friction is proportional to the normal force. So we can then substitute this in based on what we know from the normal force and this relationship and see that, substitute that stuff in, this will be mu times mg cosine theta equals the mass times the acceleration. So notice when we add friction, the mass appears in all these places as well. So again, it doesn't depend on the mass, but it is more complicated. It'll be g sine theta minus mu g cosine theta. And we could, consolidate this, factor out a factor of g, but that's our basic expression for the acceleration with friction. Okay, and then let's look at an example here. So if we look up a particular combination of materials, in this case wood, a wooden block on a wooden surface, you can imagine, notice that it'll have a coefficient of static friction of 0.4 and a coefficient of kinetic friction of 0.2. And we want to know, is this going to cause it to move? So in terms of the acceleration, really we're asking about the competition between this and this. Notice this thing has units of acceleration. We don't have to, so in other words, we don't need the mass to figure this out, but let's actually just look at the forces because I think that's maybe a little more intuitive. So what we're going to do is compare the force of gravity that's along x, that is, to the force of friction. So in other words, this is mg sine theta, and we're going to compare that to mu mg cosine theta. So based on our angle, theta equals 15 degrees, and for a mass of 5 kilograms. So if we do that, we would find this is 5, 9.8, sine of 15 degrees, versus, now let's do both mu s and mu k. So mu s, we would have 0.4 times our 5 times 9.8 cosine of 15 degrees, as well as half that, so this kinetic case. Okay, so when we do that, when we multiply this out, we find that the force Fgx is approximately 13 newtons, about 13 newtons. And the force of friction static is about 19 newtons. So what that means is that the force of static friction could be as large as 19 newtons. Remember, it's as big as it needs to be to match the applied force. So when I say 19 newtons, let's say up to 19 newtons. So what that means is that if this thing is sitting there, the force of friction will be larger than the force of gravity along the ramp, so it wouldn't move. Now, the force of kinetic friction, on the other hand, is only about 9 newtons. So what that means is that if this thing was moving, the force of kinetic friction would only be 9 newtons. Now notice this is less than the force of gravity. So what this means is if you gave it a push to get it started, it would continue to move. And I should be careful. It would continue to accelerate, really, because the force of gravity along the ramp is larger than the force of kinetic friction that would be opposing its motion. And then you could find, the magnitude of that acceleration using this expression. We could plug in our angle and our coefficient of kinetic friction and figure out what the acceleration is. So hopefully this helps connect the block on an inclined plane problem that you've seen before to what we're doing now with friction, and helps you see how this adds another aspect to it.